Hello everyone and welcome to application number 5 of our course Rational Choice Theories. So today we're going to be talking about bargaining, and more specifically we're going to be solving an example of the non-cooperative bargaining model developed by Rubinstein. So it's also called the Rubinstein bargaining game. And here we're going to consider a case where it's a finitely repeated game in some sense. So we're going to have a clear ending after a certain number of proposals. But I believe the original paper written by Rubinstein considers the infinite case, where basically players will take turns in proposing a division of the dollar and either accepting or rejecting the offer until an agreement happens. So they could play forever if no agreement happens. Okay, so we're going to consider a simple game where we're going to have two players, and I'm going to try to be quick because it's quite long and complicated, but still I'm going to try to be quick and precise. So we have player 1 who has a discount factor delta 1 and who will propose to keep X for themselves as the division of the dollar. So here, for some reason, we're going to consider the division of a $100 bill, but this would also apply to any amount of money. And this is called a divided dollar game. And then player 2, which is represented in blue in the game below, has a discount factor of delta 2, and they will propose to keep Y for themselves. And so if player 2 proposes to get Y, player 1 gets 100 minus Y. And so the structure of the game is the following. First, player 1 proposes. Here they propose any division of the $100 bill. Then player 2 gets to accept or reject. If they accept, the game ends and the payoff are X for player 1 and 100 minus X for player 2. If they reject, it's their turn to propose, and they can propose any amount between 0 and 100. And then it's player 1's turn to either accept or reject. If player 1 accepts, it's the same idea, except this time it's discounted. So if player 1 accepts, player 2 gets their proposal of Y discounted by the multiplicative discount factor delta 2 to kind of illustrate the fact that people do not like to bargain, and they would rather agree earlier rather than later, and they don't like to spend time bargaining. You can think of legal fees, of just the intertemporal value of money, but we have this discount factor, and so player 1 would get 100 minus Y multiplied by their own discount factor of delta 1. And if they reject, they get to propose again. And they get to propose again a division of the dollar, which player 2 can either accept or reject, and then the game would end after 2 proposals of player 1 and 1 proposal of player 2. So player 1 has 2 proposals available to them, and player 1 only has 1. Okay, so we're going to solve this game using backward induction. So as you know, when we use backward induction and we want to find the subgame perfect Nash equilibrium of the game, we need to identify the subgames. But here I'm going to go fast, and we're going to start with this subgame. There's infinitely many of these subgames because players can play an infinite amount of strategies, but we're not going to go into the details. Then we're going to move up the game tree and solve for this subgame. Then we're going to move up the game tree and solve for the Nash equilibria in this subgame. And then we're going to move up the game tree and solve for this subgame. And finally, we're going to do that again here and here. All right, so that's kind of the basic structure. So let's start at the bottom of the tree with this subgame. All right, so in this case, player 2 has received the offer X prime by player 1, right? And at this decision node here, player 2 has to decide between accepting the offer and rejecting the offer. And player 2 is basically comparing this payoff, delta 2 squared times 100 minus X prime, with this payoff. And here they're going to have a simple decision rule, which is going to be to accept as long as the payoff from accepting, delta 2 squared times 100 minus X prime, is greater or equal than the payoff from rejecting, 0. And they'll reject otherwise, right? So here, if I rewrite this equation, this can be rewritten as accepting as long as X prime is less or equal than 100, right? Because as long as they're getting a strictly or weakly positive payoff even, they would accept. So here, by putting this greater or equal sign, I'm assuming that when they're indifferent between accepting and rejecting, player 2 will choose to accept. All right? So this is going to be the Nash equilibrium in this subgame. Accept as long as delta 2 squared times 100 minus x prime is positive, which is equivalent to x prime less or equal than 100. And then I'm moving up the game tree, and then I'm considering the action of player 1, right? So player 1 has to decide how much to offer to player 2 for the division of the dollar, and they can choose any amount between 0 and 100. But they know that player 2 would be willing to accept any offer less than 100. So what are they going to do? They're going to offer exactly 100, right? They want to keep the biggest amount for themselves. So here, the best response of player 1 is to play x prime equal 100, because they want to get all the biggest payoff they can, and they know that any offer below 100 will be accepted. If it's exactly 100, player 2 will be indifferent between accepting and rejecting, and here we assume they would accept. So player 1 would offer $100. And here, if this game comes through, what would be the payoffs that we would kind of report here if player 1 were to propose 100 and player 2 were to accept? They would be delta 1 squared times 100 and 0. That's kind of the payoff if we reach this decision node here. All right, let's move up the game tree again. If we move up the game tree again, and then we consider the decision of player 1 at this decision node, player 1 has received the offer y by player 2, and they have to decide between accepting and rejecting, right? And here they're going to have a similar decision rule. They're going to accept as long as this payoff here is greater or equal than this payoff here, right? So here the decision rule of player 1 is going to be accept as long as delta 1 times 100 minus y is greater or equal than delta 1 squared times 100, right? And this is equivalent, I can get rid of one of the deltas, to y being less or equal than 100 minus 100 times delta 1. So 1 minus delta 1 times 100. All right? And then reject otherwise. That will be the decision rule of player 1. If this is the decision rule of player 1, right, then player 2, when we move up the game tree and we consider the offer of player 2 will choose to offer the biggest amount that would be accepted. So what's the biggest amount that would be accepted, considering the fact that player 1 accepts as long as y is less or equal than 1 minus delta times 100? It's exactly 1 minus delta times 100. So here the optimal strategy of player 2 is to offer the highest amount that would be accepted, which is 1 minus delta 1 times 100, right? And here, if this is what happens, and so it's something like something here, right? If we follow this structure, the payoff at this decision node, if we follow this structure, the payoff would be exactly player 1 gets delta 1 times 100 minus y, with y being equal to 1 minus delta times 100, which is exactly delta 1 squared times 100. And player 2 gets delta 2 times y times 1 minus delta 1 times 100. So here we see that player 2 can get a positive amount, which is slightly greater than 0. All right, and then let's move up the game tree. We have 2 more moves to consider. If player 2 considers the offer of player 1, and they think of whether accepting or rejecting, they will accept any offer such that 100 minus x is greater or equal than this payoff, right? So they will choose to accept any offer such that 100 minus x is greater or equal than the payoff they would get if they reject and they make their proposal. So delta 2 times 1 minus delta 1 times 100, right? And this is equivalent to x being less or equal than 100 minus delta 2 times 1 minus delta 1 times 100. right? So this is the decision rule of player 2, and they would reject otherwise. And finally, when we think of player 1 would they rather offer, what amount would they choose to offer? The highest amount that would be accepted by player 2, right? And here we're going to make an assumption that this amount that they'll end up getting is larger than delta 1 squared times 100. So they will choose to offer exactly x here is equal to 1 minus delta 2 times 1 minus delta 1 times 100. All right? So that's the amount that they will choose to offer in this period. And then the payoff would exactly be here, the final payoff would be x, which is 1 minus delta 1 times 1 minus delta 2 times 100 for player 1. And the payoff for player 2 would be 100 minus that, right? Which would be exactly delta 2 times 1 minus delta 1 times 100. So we see, so that's the payoff for player 1, and that's the payoff for player 2. So because delta 1 and delta 2 are typically very close to 1, we see that the payoff of player 1 in orange here is almost 100, while the payoff of player 2 in yellow is very close to 0. Okay? Because delta 2 is very close to 1, and 1 minus delta 1 is very close to 0. And so this describes the subgame perfect Nash equilibrium. So in the end, they reach an agreement very early, right? They never reach nodes in the second, third period. They just propose the highest offer that will be accepted, and then player 2 accepts the offer. All right, that's it for today. Thanks a lot for your attention.